What's cracking, guys? Aleksa here. In this video I'm doing the fourth video of the large language model series, and I'll be walking you through the BLOOM codebase. So that's the 175 billion parameter model from the BigScience event, and I'm gonna focus on showing you how the 3D parallelism is implemented in code. So that means model parallelism, pipeline parallelism, and data parallelism. So you're gonna see side-by-side comparisons of diagrams I showed you in my previous video on the ultimate guide to scaling, and you're gonna see the actual code. Just a quick recap. Here's the playlist. As I said, the first video, the ultimate guide to scaling, in that one I showed you a couple of techniques for scaling the models up to those scales of hundreds of billions and even trillions of parameters. So techniques such as model parallelism, data parallelism, pipeline parallelism, mixed precision training, and zero optimizer. In the second video, I skimmed through the papers behind the most popular publicly shared large language models such as GPT-Neo X20B, BigScience BLOOM, and Open Pre-trained Transformer from Meta. And then in the third video, I actually went through the code base behind the opt model, and I focused on showing you the mixed precision training, the loss scaling, those details, and additionally I focused on showing you how complex these code bases actually are if you want to get to these scales. So it's not just a matter of taking n, where n is the number of parameters, and shifting it from 5 to 100 and expecting everything to work. Obviously it's a bit more complex than that. Okay, in any case, as I said, I'm going to show you the model parallelism from the ultimate guide to scaling video. I'm going to show you the pipeline parallelism, and I'm finally going to show you the data parallelism approach, where you replicate the weights across multiple devices, for example GPUs, and then you do the data replication magic. So you reduce the gradients using all reduce, and then you broadcast the weights, etc., etc. Okay, enough rambling, let's get started. So first thing you have to do is obviously clone the repository. So that's the Megatron Deep Speed one. I'm gonna obviously link the link down in the video description. And just get started through this start fast README. So just follow the instructions to set up the Conda environment. And it should be straightforward, although I did experience some issues on Windows, and so ultimately I had to shift to Windows subsystem for Linux, and then everything worked out of the box. So it's kind of funny because Deep Speed is actually from Microsoft, folks, and it's not working on Windows. I guess it's a bit ironic. In any case, go through this README, download the data. We'll need these vocab and merges files for the tokenizer a bit later. Go through the training script potentially. I did go through it myself, but I decided to only show you the eval script because it contains all the necessary code for me to showcase the 3D parallelism approach. This one is complex because it additionally uses Deep Speed, which is basically built on top of Megatron, and so there is the stack of function calls is too deep, and it would be super confusing for me to show you that unless I want to teach you Deep Speed, which is not the point of this video. Okay, long story short, basically go and take these parameters for the eval script. Let me just find where the main Py script, so this one. So, and get started from here. Okay guys, so now I'm just gonna open up my VS Code. So you see here Megatron Deep Speed. I have this BLOOM 3 Conda environment, and I'm just gonna open up VS Code. So that's my IDE of choice. And let me first show you a couple of things I had to modify in the arguments here. So let me just see what's important. Again, you'll have to link this vocab file after you download it. Just create a random txt file, and you don't really have to download the wiki text dataset because this is going to work out of the box like this. And yeah, I mean, if your goal is to understand how the code works, if your goal is to actually do something with wiki text, then obviously you want to download the actual dataset. For me, I just literally pasted some random text inside of a txt file. Okay, the second thing, again, you'll have to download this file, the GPT-2 merges. I also kind of commented out this load function, and then we'll just be loading random weights, which again does not matter because I don't care about the actual result. I just care about these to step through the code and show you what's going on. Then I had this number of workers set to 0 because it's easier again to step through the code. And finally, I commented out the checkpoints activations because this does not make any sense for the eval script. So I guess that's just a minor bug on their side. Having said all of that, let's start digging into the code. So I'm going to open up the main function here, the main script. I'm going to grab the eval wiki text. So that's the config for this file that I've just showed you. And let me run this thing. Okay, guys, let me quickly go through the initialize Megatron function. Let's see what's going on there, although it's not that important for what I want to show you. Just make sure that we have CUDA, so that we have a GPU device. We set some global variables here. This is kind of interesting. So there's the, whoops, don't show this again, please. Okay, so they first parse the arguments, and let me kind of dig into that function first. So just to show you how it looks like. So the idea here is they have these global variables. So they parse the arguments, they set the, they assign those arguments to this global variable, and then it's going to be visible across the code base. So that's kind of how they went about designing this thing. I'm going to skip through the, I'm just going to maybe quickly show you how complex this is. There is a lot of arguments that go into this, but I'm going to skip all of those, and we're just going to see how that looks like when we start stepping through the code. So as you can see, a lot of error checking, and I'm going to hit F5 and hopefully get here. Yeah. Okay, so let's continue here. So that's the parsing of arguments. Then I'm going to skip this part. We don't care about that one. And then we build a tokenizer. Again, that's just going to be GPT tokenizer. You can see it here. So we're gonna kind of go through this GPT-2 BPE tokenizer, and that's a common tokenizer used throughout many code bases. And just doing this sample coding series, I realized how pervasive this tokenizer is. And I first covered it in my OpenAI clip video, so do check that one out. I'm gonna link it somewhere above if you're curious to learn more about the tokenizers. But for now, I'm just gonna basically disable all of the breakpoints and skip over the actual tokenizer. And let's continue. So we just do some padding of the vocab such that it's basically suitable to model parallelism. Otherwise, you'd have problems. And that's it. Now we just set up some TensorBoard. This is kind of cool, the code carbon tracker. So they did have this functionality where they track how much are they impacting the environment by just measuring the amount of CO2 emission. But they did comment it out. So as you can see here, they don't actually use it, but it's a cool idea, I guess. Because they say it's very unstable, blah, 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 whatever. Okay, let's step out of this and let's continue. And that's it. Okay, let me toggle on the breakpoints again. I'm gonna skip most of these things. So get args. So now this is the cool thing. Wherever you are in the code base, you literally just grab that global variable, and you're golden. You don't have to pass the arguments through the function argument list. Well, it's debatable whether that's the best thing to do, but yeah, I think it's nice. There is a couple of interesting things in this function, so I'm gonna quickly step through it. There is some initialization of the, so I'm using the NCCL, which is NVIDIA Collective Communication Library for all of those all reduce and other operations that you use to communicate and synchronize the GPUs. So it's gonna happen in this function. I'm not gonna step into it because it's fairly complex, just like library code. And then let me just see what else is interesting here. We set the random seed just for reproducibility purposes, obviously. And yeah, that's it. And then in the compile dependencies, there is a couple of interesting things going on. Again, we are going to, so first there's some, this part is not that interesting, but there's one part where they load certain CUDA kernels, and we're gonna later actually use them and leverage that C++ code for extra performance. So I'm gonna skip through most of these. We actually saw something similar, if not the same. Actually, it's the same code because opt was also using Megatron. So my previous video was also using Megatron in the background. So we've seen the same code here. So what we do is we load these kernels. I'm gonna step into it quickly and just show you how it looks like, but it's nothing super crucial. I mean, not related to the 3D parallelism in that sense. So here you can see we're just loading various kernels for like scaled upper, for softmax, and then for some other softmax and LayerNorm, etc., etc. So I'm gonna put the breakpoint here, hit F5, and just exit here. So it was more of FYI than anything else. Okay, there is some barrier function call, which basically synchronizes across. So all of it basically waits. All of the different devices, GPUs, will wait at that line until the other GPUs hit that same line, and then the barrier is going to release the execution across all of the devices. That's what the barrier does. But I have a single GPU, so that's not interesting. And even though I have a single GPU, I'm still going to be able to show you the 3D parallelism, as we'll soon see. Okay, let's just exit here, and that's pretty much everything I wanted to show you. Now let's get into the main script. So because I'm using wiki text 103, I'm gonna take this particular main function, and then let's now enter here. Okay, so we fetched the arguments, and let's see what's going on. So because we are using wiki text, we're gonna set the eval metric to loss. That's not that important, and this is where stuff becomes interesting. We're now going to see how the parallelism is implemented in the code here. Okay, so let me re-enable the breakpoints, and let's continue stepping through this. So here's the model provider. So we enter this get model function. Let's now see what's going on. Okay, so we hit this else branch, and now because I have a single device, and because of that, my pipeline is only of length 1. I have a single stage, and that's why both the pre-process as well as the post-process here are going to be set to true, as you can see here. But if this was on a, if you were running on a let's say a 2x2 topology setup, so we have 4 GPUs in total, and I'm going to use that topology as a running example. Let me kind of open up the OneNote and show you what I mean. So let me go here, and this is going to be the running topology I'll be using. So basically, I'm going to have something like this. So we have a GPU here, we have a GPU here, we have another GPU here, and we have yet another GPU here. So we're going to have 3 types of parallelism, but I'm going to show you only the model and the pipeline here on the image. So these ones here are going to be stage 1. So stage 0, and this is going to be stage 1. Okay. So basically that means we'll have half of the layers of our transformer being here. Maybe if we have 24 layers, 12 will be here. So we'll have 12 layers here, and we'll have 12 layers here. Next up, I'm gonna do something like this. So we're gonna have model parallelism. So across this dimension, we have MP, and across this dimension here, we have pipeline parallelism, PP. Okay, so this one is gonna be 0 and 1. So this is gonna be the topology that I want you to have in your mind, and we'll see how it's gonna be useful in a couple of minutes. Okay, again, keep in mind that in the setup I just showed you, the devices from the stage 0 of the pipeline parallelism will have, this will be true and this will be false. And then the second stage will have, this will be true and this will be false. And if you have even more stages, then some of these devices will have both of these pre and post process flags set to false, because they are neither the first stage nor the last stage of the pipeline. Okay, hopefully that makes sense. Now let's enter this function here. So yeah, we just set this to true because we are dealing with loss metric. Let's continue, and here's the GPT model. So I'm going to be using the GPT transformer as the underlying architecture. So let's enter here, and let's see what's going on. So it's going to inherit from a Megatron module, which is a light wrapper around Torch module. So I'm not going to step through the constructor. Let's fetch the arguments here, and let's just kind of skip across all of these details. This is the interesting part, the language model. So now we're going to enter that function. And here, okay, again, we just fetch the arguments. We continue here. Now there is a transformer language model. So that's going to be an interesting one. So let me hit F5. Let's get here. So it's inheriting again from the Megatron module. Okay, we can step across all of these. I'm going to focus only on the parts that are interesting. So here's the embedding. This is the interesting part. So let me kind of put a breakpoint here, hit F5. let's see how this is going to work. Okay, so the embedding table is gonna have a couple of details. So here's the vocab parallel embedding. That's what they're using in the background. Parallel suggests that we are basically gonna do a model parallelism of this embedding table. And by the way, let me just go back a step up here. You can see that we only enter here if the pre-process is set to true. And that's only true for the first stage in the pipeline, or 0th index, as I kind of made the notation. But like the first devices in the pipeline will only have this embedding table, which makes sense, right? Because we want to split the model layers across different stages. Okay, so let's get back here. So here is the vocab parallel embedding. Let's enter here. Let's gonna hit F5. Oops, let me hit F5 and enter there. Okay, so again, let's see what's gonna happen here. So this is the interesting part. This get tensor model parallel world size is going to, in the topology that I showed you a couple of minutes ago, it will return 2. So for my particular setup, it's obviously going to return 1 because I have a single GPU, but in general, it's going to return 2. And now let's see what's the repercussion of that. So here, what happens is we fetch the rank, so the tensor model parallel rank, and that's going to be 0 for the basically devices here. So it's going to be 0 for these devices. It's going to be 1 for these devices here. Okay, so let me go back to code. Now, with that in mind, and having this thing, so this is this is going to be 2 in the example I'm showing you. Let's now enter this function, and let me show you what it does. So it takes the global vocab size, which is this big 50K slots in the embedding table, and we're going to divide it by 2 because our model parallelism world size is actually of size 2 in the running example I'm using. Okay, so it will be something like 25K here. Okay, and then what we do is we enter this function here, and you can see here, so for rank 0, we would have this thing would be 0 because we multiply by 0 25K, and then this would be 25K plus this would be 0 plus 25K, so that would be 25K. So that means we would return 0 and 25,000 here as a result. Obviously, in my case, I'm returning 50K, but bear with me. Okay, so that's the first thing we need to understand. Now those variables are going to be used to split the embedding table across multiple devices. That's the whole point. So now you can see here, the number of embeddings would be 25,000 if we had the topology I'm using. We can skip this, we can skip this. Those are just that's the bits and bytes or something, basically where they use integer 8 precision, etc., etc. We're going to ignore that in this video. So here is the interesting part. So now we create the weight of the embedding table. So we can see here, we are passing this variable, which would be 25,000 again, and we're passing the embedding dimension, which is 1024, blah, blah, blah. That's it. But the weight would be, as you can see, 25,000 times 1,000 on one device, and on those devices that have a rank 0, and then it would be additionally 25,000 for those devices that have rank 1. Again, talking about model parallelism here. Okay, so we just now initialize it, and that's it. So now you've seen for the first time how the model parallelism looks like. So let me just exit here. Let's now continue. The second thing we want to do here is create some positional embeddings. Now these, because they are much smaller than the vocab embedding table, they're just going to allocate the whole thing across all of the different devices. So we have like complete, we can see here 1024 because that's going to be our sequence, and that's how many positional encodings we need. Okay, let's continue. We just initialize those, and let's see now what's happening here. We can skip all of those. We just add some dropout, blah, blah, blah. I keep entering this function. I'm not sure why, but we now have the embedding, and let's continue. Now let me just update the diagram here. I think this is going to be useful. So let me just take some different color. So we have the embedding table currently placed like this. So we have embedding table here, and we have embedding table here. And the size here is 25K, and the size here is 25K as well. Okay, let's now go back to the code. Now we have the parallel transformer. Let's see how the transformer is going to be split. Okay, so let's enter the parallel transformer, and here it is. Okay, again, skipping these details until we get here. So here is an interesting assert. So the number of layers has to be divisible by the world size for the pipeline parallelism. In the running example I'm using, it's going to be 2. So that means you have to be the number of layers has to be divisible by 2. In my actual setup, I have this will be 1. So yeah. Okay. Now this is the interesting line. So we see here that we divide the number of layers by the number of stages. And again, so because we have 24, that means we would now have 12 layers being allocated on this particular device. Okay. So again, keep in mind this code. So the thing I'm just stepping through, this same thing would be happening in parallel on 4 devices, and each of those devices have different contexts because they lie in a different part of the topology, and because of that, they will be entering different types, different code. They will be going through the different code paths. That's the main idea. Hopefully you understand that. Let's continue here. Okay, so now we create the offset. So we grab the rank and we multiply it by the number of layers. So that means that the offset for these 2 devices here is going to be 0. For these 2 is going to be 0, and for the 2 ones here is going to be 12, right? So let's go back here. So it's going to be 1. The rank will be 1 for those, and then times the number of layers, 12. So offset is going to be 12 for them. So let's see how offset plays a role here. So we now form 12 layers, and we have the offset here. So you can see that we are passing that index information into this build layer function. So let's enter the build layer function. Here it is. And there we start building the actual transformer layers. So we'll do this 12 times. So let me just enter this layer here. Let me hit F5, and we are here. So again, let me just focus on the important parts, ignoring many details, obviously, otherwise it will be too bothersome. Okay, so first things first, we want to instantiate a LayerNorm. Okay, let's see how the LayerNorm looks like. The LayerNorm has some fused components, which is interesting. So that means we'll be using optimized CUDA kernels, fancy word for saying functions, implemented in CUDA library that are running super fast on GPUs, obviously, on NVIDIA GPUs. So here you can see we import this fused mixed precision LayerNorm CUDA. So let me show you where that was constructed. And I actually showed you that in the beginning of the video. So here, let me just move this thing here. So if I were to copy paste this here, so you can see here we are loading that precise variable is loaded using this CPP extension load helper. So we kind of passed, I kind of showed you this function before, and that's where it was initialized. Now let's get back to the actual code. Let me go to the top of the stack. We import that kernel, and yeah, we're gonna then use it a bit later. So everything else is not that interesting. I'm not gonna focus on the LayerNorm because this one is not going to be split across devices. Okay, let me exit this, and let me just kind of move this a bit to the left, and we are out. Now let's see the parallel attention. This is gonna be the interesting part. So let's enter the parallel attention. I'm gonna hit F5. Let's go to the part that we care about, and that's the part where we split. So here we can see, we can step over all of these. The magic starts happening right here. So again, model parallel world size is gonna be equal to, so it's gonna be 2. And now we divide the projection size by 2, blah, blah, blah. So just dividing number of attention heads to 2, by 2, and now we get to the interesting part. So this is the column parallel linear feed-forward layer. That might be a mouthful, but let me remind you what that is. So this is what we are actually building right now. This is the self-attention layer, and what we are building right now are these, as you can see, column parallel layers. So we take the weights and we split them in this column-wise fashion. And then we're gonna use these here. The Q1, K1, and V1 are going to be used here, as you can see. And then the Q2, K2, and V2 are going to be used on the different device. And that's what we are currently building. That's what this code is implementing. So let me enter the actual column parallel linear, and you can see again the weight matrix is being split in this column parallelism fashion. So let me hit F5, let me enter here. Let's see where that's going to happen. So here's the world size. Again, this is going to be equal to 2, and then the output size is going to be divided by 2. Okay, so let's continue. And here is the actual, so we are now allocating the weights. This is going to, so this would, if we had the topology I'm using as a running example, this would be, as you can see here, divided by 2. So that means we're literally splitting it column-wise. That's the whole point, okay? And then once we have those weights, we just initialize the weights, and there's some bias. Let's skip that part. That's not that interesting. So let's exit here. Again, entering this thing. Okay, so that's the first part. Let's see what else. So now we have to create some softmax stuff. That's going to be this part, the softmax. The only difference is this is going to be optimized. So obviously there are no learnable weights in this one, so I'm going to just skip it. We're not sharding it. So now we create the dropout, blah, 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 and there is the row parallel linear. So this is the second component. So let me go back again to the OneNote, and here is the second part. So here you can see the other part of the self-attention layer. We have this linear layer, and we split it row-wise this time, B1 and B2. So you can see here. So let me go back to the code, and let me enter the row parallel linear. So if I enter here, you can see again the diagram. And let me put a breakpoint here. Let me hit F5. So here we are. Again, world size is going to be 2. And let me continue. And again, this time, you can see that the input size per partition is the one that's being divided. So here, the input would be divided, not the output size. And because of that, we are doing row-wise splitting, right? That's it. That's the difference. Again, I'm going to skip everything else here. Let me kind of step out of this function. Shift F11 does that on Windows keyboard. And here we are. So we have the row parallel linear instantiated. Let's continue. We don't have rotary embeddings, so we can skip this part as well. And here we are. So that was the parallel attention. Okay. Again, let me just update the drawing. We have the parallel attention being sharded across 2 devices in this running example. So that means we'll have half of the weights here and half of the weights here. Obviously, we'll need 12 of these. So I kind of didn't do it justice here, but yeah, you can imagine we'll have 12 of these transformer self-attention layers. So let's go back to the code. Let me exit here. So we have LayerNorm again. I won't bother. I'm just gonna exit this LayerNorm. Let's see what else. We skipped the decoder part. So now there is the parallel MLP. So again, how the transformer block looks like. We have the self-attention module, and then we have the MLP part. So now here we'll see first the column-wise splitting and then the row-wise splitting. So this is the diagram we'll implement. Let's go back to the code. Let me show you this quickly, and then this is the last thing I'll show you, and then we are pretty much done with this model construction. So let me hit F5. Let me enter here. So again, column parallel, and I'm just gonna skip. I'm just going to disable the breakpoints because it's the same logic as before, right? We've seen this. This is the same logic as before. So I'm just gonna skip over all of that. Let's get here. Now some activation stuff. Here is the row parallel linear, and that's it. And that's the one that has the 4H usually is the common convention. So the hidden layer will have 4x more weights than the input and output dimensions. Sorry. Okay. Again, let's exit here, and that's our basically transformer layer. Again, you can always follow here where we are. We're currently implementing the transformer layer. So I'm gonna exit here, and we do this 12 times. So I'm gonna, again, let me just make sure it's disabled. I'm gonna enable the breakpoint here, hit F5, and we have 12 layers. So again, let me update the drawing. Here is the drawing. We now have 12 layers here and here. So we have 12 layers here and here. And obviously, because this is running in parallel, these two devices would also have 12 layers here. So 12 layers and 12 layers. The difference is these two, because they are in the rank 0 of the pipeline parallelism, they additionally have the embedding table sharded. Cool. Guys, let me know how you like the video so far. Leave any feedback if you have any. That would be super cool. So again, post-process. That's going to be active only on the last stage of the pipeline. So that means only those devices will have the LayerNorm, but I'm gonna skip I won't enter the LayerNorm because we already seen it. That's the optimized LayerNorm. And that's it. Again, that was the parallel transformer. Let's continue. We don't have the decoder part. We don't have the pooler, so we can exit here. We can exit here, and we have our language model being constructed. Again, I'm not sure why I'm entering this thing. So once I enter it, I just do step out, and that's how I exit, in case you're wondering. Okay, guys, here we are, GPT model. We just constructed it. Now there is this initialized word embedding. So because I have, in my actual setup, I have a single GPU, so I'll just hit return. But in general, if we had the actual topology I'm using as the running example, we'd be hitting this code here. And let me show you why this is interesting. So they mention it here. So parameters are sharded between the word embedding, are shared between the word embeddings layer. So that's the common thing you always do. So you have the embedding table being shared between, so mapping the tokens into the embedding vectors. And then at the output, you also use that embedding table to map the embedding vectors into the vocab. So basically distribution across the various words, subtokens from your, or tokens from your vocabulary. So those are tied, and you can see here they have a nice trick that they do. So if this was running on the last stage of the pipeline, then they would create embedding table. Again, it's going to be a parallel embedding table. So that means it's going to be sharded across two devices of the last stage of the pipeline. And then this is the nice trick. So basically, what they do is they do all reduce. So ensure that first and last stages have the same initial parameter values. So because this was now independently allocated, and because they are lying on different devices, because of that, they have to do all reduce. So you can see here, if we are hitting either the first stage of the pipeline or the last stage, apply the all reduce method on this word embedding or word embeddings weight. If you're not familiar with these collective operations, I did not explain them so far, just check out the wiki page. They have a nice visual explanation. It's fairly simple. Roughly what's going to happen is, assume that the first stage will literally receive the weights from the last stage, and then they're going to divide it by 2. And if the last stage does the same thing, you'll end up with the same result, and that means you'll have the same weights both in the first stage and in the last stage, and thus you've synchronized the weights. As simple as that. Okay. Guys, hopefully that was interesting, and hopefully that makes sense with the drawing I'm using in OneNote. So let me exit here. So here is the now some stuff that's not that vital. I'm going to skip all of this, put a breakpoint here, hit F5. Let's see what else. So we push all of these models onto the GPU. We use this float, we convert them to float 16 weights. So I'm going to just basically, let me enable the breakpoints now. So I'm going to hit this one a bit later, so we'll see how that is going to be used. Okay, local DDP, data distributed parallelism. We're going to ignore that for the time being, and let's just return the model. Okay. So again, because I have load set to none, I will not be loading the checkpoints, which means I'll basically be using random weights. Okay, now we build the dataset. Let me quickly walk you through this one, although that's not that relevant. So tokenizer. So again, I just load this random dummy file I created. And you can see what it has. It literally, I copy pasted. I actually took a single paragraph from wiki text dataset and just copy pasted it a couple of times just to have something there. So now we just do some processing, detokenization, blah, blah, blah. Okay, let me just exit here. This is not interesting. So we then tokenize the text. Okay, I'm just hitting the breakpoints. So this is some processing that they do. As you can see, a lot of details that I'm trying to unsuccessfully ignore. So we now do the tokenization, and you can see here, now we have the, let me show you how that's gonna look like. Tokenized data is just a list of tokens of our text. So the text was tokenized, and we have 448 tokens, the smallest data set ever. Okay, now we use that to construct this LM data set. Again, I'm not going to dig into a lot of details because that's just the language modeling detail, and we are trying to focus on the 3D parallelism in this video. Okay, let's exit here. We have the data set. Now we built the data loader. The reason I'm going to show you this one is because it involves the data parallelism approach. So here it is. In PyTorch, it's fairly trivial. So here you can see get data parallel world size. So now additionally, I did not show you this so far, but imagine having this same group of devices, like 4 devices like this. So let me just change the color. So imagine having this same group duplicated maybe twice or even 4 times, okay? And we're doing the same thing in each of these groups until now. So now it's gonna be a bit different for each of these groups. Okay, so let's say this is group 0 and this is group 1. I'm gonna ignore, we're gonna have 2 groups, okay? So let's go back to the code. We would get world size would be 2. And let me show you how this is implemented in the background. It literally calls this distributed get world size, and then you specify the particular group. So here they specify the get data parallel group, and that's why basically they get number 2. Okay, some constants there. I will not dig deeper than that. Let's continue. Let's get the rank. So now whether the rank is 0 for the left group, so rank would be 0 again for this group here, and it would be 1 for these devices here. So that's how we'd have a differentiation. Let's continue. We form the distributed sampler, okay, and that one is going to be shifting a part of our batch to one group and the second part to the other group. So that's kind of handled in the background by the PyTorch. Okay, so now the data loader, blah, 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 pinned memory. Again, a lot of details, I'll have to skip those. And now we enter the evaluate and print results. So here is the actual function where we'll be doing a feed forward pass through the model. So we just set it to eval mode. We enter the torch no grad context because we're doing inference. We're not trying to train anything here. And now we're going to fetch our first batch. So I'm going to ignore how that works. So I'm going to disable the breakpoints. Otherwise, I would hit some breakpoints I left there. So let me hit F10 and we have a batch. So a batch is simply going to be, as you can see here, we have text and we have pad mask keys. So text is going to be, I guess, 8 times 1024 or something. Yeah, so 8 because we have a batch of size 8, and 1025 because our sequence that we're going to pass to the transformer is going to be 1024, but it's 1025 because we'll be using 1 as the target. And so you're going to see that in a second. So yeah, hopefully that makes sense. Like you literally take it's 1025 because you take the first 1024 as the input, and then you're trying to predict shifted by 1 to the right. You try to predict that sequence, and that's why you have 1025 here. Okay, let's continue. Let's enter the forward pass. Let's see what's going on here. So some batch processing. Again, I'm going to ignore all of that because that's just language modeling standard stuff. This is the interesting part. So this is the receive forward. So what's going on here? So let's enter there. Let me now enable the breakpoints. So here what happens is the following. So if we are in the first stage, then the input tensor is none, okay? But if we were in some other stage, then we call this communicate method, And that means we're waiting for the output of the previous stage to pass that output as the input of this stage. And if that happens, we're going to override the batch that we just loaded from the data loader. So that might be a mouthful. It's gonna hopefully make sense in a couple of minutes. So here is the input tensor. Let's continue here. Okay, some unwrapping of the model, not that interesting. So here's the part where we set the input tensor. And let me kind of dig into this. So blah, 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 we call the GPT model set input tensor function. And then, okay, let me exit this one. So then we enter the transformer language model set input tensor. Again, a lot of levels of indirection, and I keep hitting this random function. Okay, so here we are. So finally we get to parallel transformer and we set the input tensor to none because we are now in the first stage. I mean, at least in the actual setup I have. But let me show you where this one is used. So it's going to be used here a bit later in the forward pass. And we'll see that if pre-process is true, that means we're in the first stage. And in that case, we'll actually be taking the data from the batch. Otherwise, if we are not in the first stage, we'll be passing the actual input tensor that's passed from the previous stage. So again, we'll see that a bit a bit later. So let me now exit all of this. Let me exit this. Let me exit this. And let's continue here. So here is the actual forward pass. Again, just so that we are on the same page, let me show you what's going to happen here. So what's happening is we are having our distributed data loader fetching a batch, and I'm just going to simply draw it as a simple 2D square. And we're going to basically divide it into two pieces. This one is going to be passed to this group, and the first chunk is going to be passed into the 0th group here. Okay, and now what happens is this is going to be fed here. And while that's happening, these two guys are blocked. So the thing is, that communicate method I showed you is a blocking method. So that means until this has done its feed for, so until this data has passed through the first stage, these guys are waiting, and then only then do they start doing the actual computation. That's how this is going to look like. And obviously the same happens for the rank 1 for the second group, second data parallel group. So I will not be drawing it there, obviously. Okay, let's enter the feed forward pass. Okay, we have to enter this forward call. So distributed blah blah blah. There is a lot of levels of indirection again here. Let me just exit here. Oh my god. Oh my god. Let me enter here. Okay, so finally we are in the forward pass of the float 16 module. So let's see what's happening here. So as you can see here, if we're in the first stage of the pipeline, we convert our data to float 16 because we're going to do mixed precision. So now inputs are going to be converted to float 16, and now we call the actual transformer with the float 16 data. Okay, let's enter here. Let me hit F11. I think I can just hit F5 and I'll hit the, yeah. So here we are. We are in the GPT model forward pass, and let's start going through it. Okay, so again, I think I can hit F5 because I have a breakpoint there. Yeah, so we are in the transformer language model. Okay, so as you can see here, only the first stages, because pre-process is true for first stages of the pipeline, are going to do the embedding part. Okay, so we do the embedding part. Let me kind of enter this. Whoops, I hate this. Let me enter it. So here we are in the embedding forward. Let me see whether it's useful to enter this one as well. So here we are in the vocab parallel embedding. Let's see how the forward would look like. So again, keep in mind that we have sharded that embedding table here and here. So we only have 25,000 of our embedding vectors here, and the other 25,000 is here. So they'll somehow have to communicate between each other, such that we can end up with the correct results. So let's see how that's going to work. So let's enter here. So we would actually be entering this branch if I had the setup that I'm using as running examples, because the model parallel size would be 2. So what would happen is the input mask, as you can see here, it would be true for all of those indices that are smaller or bigger than the index here. So then the boundary index here, and these would be 0 and 25,000 for this one here, and 25,000 to 50,000 for this one. Okay, and that's why this is gonna mask those indices that do not belong to this device. Okay, so there is this subtraction here that we have to do so that we have correct results, because imagine we are now on this device. Because its start index is 25,000, we want to subtract 25,000 such that we end up with 0, because we are indexing in its table, and the 0 index is the first slot in that table on that device. If that makes sense. Sorry for being a bit confusing here. And you can see here, for all of the other indices, we just set them to 0. Maybe let me try and draw this quickly. So here is what's going on. Okay. We have basically input that contains indices from the whole table. So that means it might have numbers. Okay, let's quickly check what's the actual size. So let me use this input as the running example. So we have shape 8,024. Okay, so let's imagine we just have 1,024 because we have batch size of 1. It's going to be easier. Okay, so here we are. So we have a vector that's like 1,024. So this is going to be 1,024, okay? And it might contain in any of these slots, in any of the dimensions, let's say this is dimension I, it might contain numbers from 0 to 50K. I'm just going to round the numbers because it's easier, okay? So now let's assume we are on this device here. Okay, so that device only has the following indices. So we have two tables. This one contains from 0 to 25K. And this one contains from 25K to 50K, 25K to 50K, okay? So what this device is going to do is it's going to mask all of those values here. So let me take a different color. So all of those values that have numbers that are 0 to 25K, because it does not contain those numbers. So it's going to mask them out by putting them to 0. So let's see, this one is also put to 0, this one is also put to 0, blah, 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 okay? And then it's going to take this number here. Let's say this one is 26K. It's going to subtract the 25K because that's the offset. And we're going to end up with 1K. And 1K, when you index with 1K into this table, you end up with some vector, embedding vector here. And that vector is, if you take a look at the whole table, is at the 26K. Okay, so that's why we do all of this offsetting. Hopefully this now makes a bit more sense. Okay. Let's continue. So now we do the embedding and we get the results. Okay, so let's check out the shapes. Shape is going to be 8,024, 1,024. This is the sequence length. This is the embedding dimension. And now what we would have to do is we would have to set those vectors that were masked out to 0. Otherwise, they would have incorrect results. Okay. And finally, what we do is we call this reduced from tensor model parallel region. Let me quickly enter this one, and then I'm going to show you what is going on here. So here we are. Let me just go like this. So let me actually enter here. Let me enter here, reduce, and here is what's going to happen. In case that that we have multiple stages, sorry, this is model parallelism. In case that we have multiple shards across, if we have model parallelism of size 2, as the running example is using, then we would not enter this line. We would do the all reduce across the group of across the model parallel group. So let me break that down, what we have done right there. So let's again get back to the drawing and let's see what happened. Okay, so because these guys here were masked out, so that means this one was maybe 14K, and we've artificially set its value to 0. Because it was 0, that means it was indexing the 0th vector from this table, which is incorrect because we want the 14,000, right? So this one here, again, let me just change the color and let me explain. So this one here was maybe 14K. So that's the token ID, okay? So that one was indexing somewhere here, but because we've set it to 0, it was actually indexing this vector here. And that's why we have, oops, it's glitching. That's why we had to do the zeroing out, because we don't want to have this value here. We don't want to have this embedding vector for this particular token. That's why we do the zeroing. That's why we do this part here. And then what the all reduce does is the following. Let me go back here. So this is going to happen. Let me see whether I can explain this nicely. Basically, this device here mapped this set of tokens into obviously various bunch of embedding vectors. So the dimensionality here is the same as the dimensionality up there. So it's 1024. But here we now have the hidden dimension. Okay, so this vector here is going to be valid for this device. So that vector is going to be valid. So let me change the color to green. So this one here, this token is going to be valid on this particular device. Okay, so it's valid here. But as we just saw, it's going to be invalid for this one. Okay, so let me draw another table. So let me draw the result. So this is the output from this device. So this is the output from the second device. And it contains a corrupt data, actually all zeros, because we've zeroed it out. So it's going to be all zeros. And so now what the all reduce does is basically you sum these up. If you sum them up, you'll end up with a correct result both here and here. Because if you just add zeros onto this device, you keep the same value. But this device will now have the correct value of the embedding vector. And that's the magic of the all reduce. So what's going to happen is these GPUs here are going to do that type of a communication and update the embedding vectors. So that's a beautiful thing, like if you ask me. So hopefully I managed to explain it nicely. And now finally, let's get out of here. Okay, again, just to update our mental model. So where we are at the moment is in the state where basically these two devices here are waiting for the information. And we have the embedding vectors on this device and on this device being the same because they're synchronized because of this all reduce we've just done. Okay, so we are now there. We have that, and now let's get back to the code. Okay. So after this, we're gonna have some positional embeddings being added. That's less interesting because it's not sharded. Let's continue. We had some dropout, blah, 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 and we end up with the output, okay? So now let's see what's going on. So we now do the call to the encoder, and that's just going to be our transformer, basically. So let's enter there. Let me hit F5. So we are now in the parallel transformer. Let's step over all of these. If self preprocess. So again, if we are in the first stage, we'll be doing this. So if we're in the first stage, we'll be grabbing the embedding vectors we just created. So let me show you the shape. 8024 to 1024. And we just grab those. We do some transpose operation. We do contiguous, and we continue. But if you recall this line here, this was from the, if this was not the first stage of the pipeline, but instead, if this was maybe second or third or whatever stage, then instead we'd have hidden states being equal to input tensor, which came from the previous stage, okay? So we would bypass this part here. Hopefully that makes sense. Let's now continue. We're not doing checkpointing. Okay, now we are just going to do a feed forward through all of the transformer layers. Okay, so let's do that. Let's grab so here's the layer. I can hit F5, I think. So we are now in the parallel transformer layer. And the first thing we do is we pass the data through the LayerNorm. Let me quickly show you how that's gonna look like because it's fused. Oh my God, this sucks. Okay, so let's just step over here. Okay, here we are. And here is the fused LayerNorm affine function. We call this apply method. So let me enter here. So here you can see how it looks like. Oops. So what it does is ultimately it calls this CUDA kernel, which is a global variable which we loaded in the beginning of this program. And then we just call the forward affine. So we cannot actually enter here because it's just a compiled C++ code. So I cannot enter with this current debugger. Maybe there is maybe it can be tweaked so we can enter and see the C++ code, but I'm not sure how that will work. Okay, so in any case, I just wanted to show you how the kernels look like. Now let's exit from the LayerNorm. And now let's hit the actual attention part. Okay, let me hit F5. here is the attention part. So we are in the parallel attention part. Again, remember the weights are sharded such that each of these devices in the rank 0 and rank 1 of the model parallelism only have a portion of the weights. Okay, so we end up with some okay, so we first hit the column parallel layer. Let me go back up again here up the stack. So we hit the query key value is actually the column parallel layer for a function. So that's, again, let me show you here. So we are hitting the column parallel. This is the part I was showing you. So let me go back to the code now. And let's see what's going on here. So we call this weird function copy to tensor. So what is it doing exactly? Let's maybe enter. So let's enter here. Let's enter here. And you can see here in the forward pass, it's just doing identity function. So why are we doing this? Well, that's because in the backward, we'll be doing the reduce method. We'll be calling the all reduce. So let's see why that makes sense. Let me show you the diagram here. It's kind of clear once you see it. So what we're doing here is this. We are implementing f. F is, as you can see here, it's just an identity function in the forward pass because we just passed the data, the same data x, to one device as well as to the other device. But once we go backward, we want to all reduce the information. We want to all reduce the gradients that came from this portion and this portion. We want to basically average them and then pass them to the previous layers. Hopefully that makes sense. That's why we have it implemented in such a way. Let's now exit this part. Now this is less interesting. We just apply the actual linear layer and then blah, 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 bias. We can exit there. That's less interesting. Okay, so now we just have some, what's this? Reshaping. We have some view, blah, blah, blah. We're splitting into 3 parts, the query key values. I'm not going to focus on the actual transformer logic because I do assume you either know that, or even if you don't know, just focus. Let's focus on the 3D parallelism. So again, just some transformer stuff. We're changing the views so we can do multiplication between the keys and the queries, and then basically use that to. Okay, so here we just pre-allocate a tensor that's going to contain the scores for that will then apply the softmax. We'll then apply a softmax, as you can see here. So we first do the multiplication of queries and keys here, so we can skip all of that. And then we now have attention scores, and in order to convert scores into actual probabilities, we have to apply the softmax. So again, I'm gonna exit this softmax layer. It's not that interesting. We've already seen the CUDA kernels, so I'm gonna just skip that. Okay, attention, we just do the dropout, blah, blah, blah. Let's continue. My computer is kind of struggling. You can see it's kind of lagging behind, so I cannot go faster than this. We just do some, again, view manipulation, and then we do the batch matrix multiply, which is going to basically sum up the value vectors, and we end up with the final result here. And then we just change the view, we do permute, blah, blah, blah. Nothing new there, hopefully. And finally, we hit the dense part. And the dense part is, let me show you here. The dense part is this part, so that should be the row parallel linear layer, right? Because we're splitting we are now here. We're now here. Let me go back to the code. Let me enter here. Whoops. Let me enter here. Oh my God. So we are in the row parallel linear layer, as I said. So let's quickly see how it's going to work. Again, a couple of details there. So you can see we first applied the linear layer, and then we call this reduce from tensor model parallel region. So let's see how that thing looks like. That one in the forward pass is doing the all reduce, and in the backward it's just doing the identity function. So it's just literally the polar opposite from what the column-wise was doing, right? So let's go back here. And why is that? Let me show you the diagram again. So here you can see in the forward, we want to all reduce these weights such that we end up with the correct result on both devices. But in the backward, we're just copy pasting the gradients. That's the reason why that was implemented in such a manner. Okay, so I'm gonna skip all of this because it's not relevant, and we are done with the parallel attention. We are exiting the attention right now. And okay, now we have some residual stuff, blah, 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 biases. We don't care about those. Some of those are JIT compiled, so we wouldn't be able to step through it either way. Post attention LayerNorm, I think we're gonna hit the breakpoint here, so I'm gonna remove it, exit this function. Let's exit the function here. And we're back. So we don't have decoder. Now we hit the MLP. So MLP is gonna be this part. Again, we're gonna now pass the data that came out of this part. We're gonna pass it here, and we're gonna repeat the same thing. So I'm gonna skip it. So we're gonna do the as you can see here, column wise and then row wise, but it's the same logic. So we can safely skip this part. Okay, so let me do disable all breakpoints. We do the same thing, and that's it. We are done here. Let me just exit this part here, and let's return back the value. And that was the layer 1. We obviously repeat that 12 times. So I'm going to put a breakpoint here, hit F5, and now we're here. So let's see where we are now here with the diagram. So the data has successfully propagated all the way. Let me change. I'm not sure what color is the best one here. So maybe let's do it like this. So we are now here. We successfully propagated our activations all the way to here. And now we'll be passing them slowly to the second stage of the pipeline. So let's go back to the code. In case we are in the last stage of the pipeline, we'd be doing this additionally, passing it through the layer norms. And that's it. We are now here. We can step over all of this and we return back the results from our transformer language model. Guys, this is pretty much it. This is, we've seen the main concepts already. There is now a couple of additional details here. So like post language model processing, what's this one? Let me enable the breakpoints. Let me hit F5. Here we are. So again, there's going to be some synchronization between the devices in these ultimate parts. So yeah, assume now we're going to project those weights into the vocab space. So let's see what's going on. So we have input parallel. That's going to be, I guess, 8,024, 1,024. Yep. And then once we do step over, we're going to end up with the vocab. So 1,024, 50,304. So that's it. Again, there was some communication happening here between the devices such that we have consistent results on both devices. And that's it. Let's continue here. Whoops. We're now almost at the bottom of the stack. So we're now in this float 16 module. What we now do is, because we're in the last stage, if we're in the last stage, we convert from float 16 to float 32, and then we return back the results. Okay, so let's exit here, and we are back. So again, now we're gonna have this send forward function, and you can see here, if it's not the last stage, then communicate. So that means all of the stages will have to pass the data to some other device unless you're at the last stage of the pipeline, which makes sense. Again, communicate is a blocking method. So that means if you're waiting for the data, you'll be blocked. That's why you have the concept of micro batches, so that you can minimize the waiting, the idle time of the devices. Hopefully that makes sense. Okay, so in the last stage of the pipeline, you do this additional vocab parallel cross-entropy, I can quickly maybe enter this one, although I think it's going to be fairly detailed. There's a lot of details here, but like the concepts are the same, like nothing new there. So I'm going to slowly step out of all of this. So yeah, as you can see, devices have to communicate such that we end up with the correct logits, and then blah, blah, blah. You can go through this one at your own pace. I think it should be fairly easy to understand it. Okay, let's exit that part. Let me exit it, and that's it. We just do some summation, we return back the loss, we do some additional all reduce here, and now we keep on doing this. Ultimately, you'll end up with the evaluation metrics. I'm going to disable the breakpoints, hit F5 here, and exit here, and now let's exit from here, and that's it. Now if we're on the last rank, we just, and by the way, here's how the last rank is calculated in this particular example. So here you can see that we just get the rank without any group, which means that now however many devices we have like in total, we just find its absolute rank. So that means that, for example, this one would be rank 0, this one would be rank 1, 2, 3, then 5, 6, 7, 8. We will be returning those results. So basically, we only on the last rank, so only on a single device in our whole cluster, we do this operation. So basically, yeah, just some blah 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 perplexity, and then we print the results, but we don't care about the actual results. So yeah, so you can see here average loss, perplexity, adjusted perplexity, blah blah blah. Nothing interesting there. And now finally we're done. Okay guys, we've seen a lot so far. Let me do just a quick recap and then we can wrap this video up. So we have a couple of differences depending on whether we are dealing with the last stage of the pipeline, with the first stage of the pipeline, or the intermediate stages of the pipeline. So let me go and run the eval script again. So I'm gonna hit run here, and I have a breakpoint set inside of this forward step function. There's a couple of things I want to explain here. So first things first is this receive forward function. Then I'm going to explain the differences in the forward pass through the model, and then the send forward part. So first things first, here, if we enter, you can see that the first stage in the pipeline will have the input tensor set to none, as you can see here, which means that they'll actually be fetching the data from the data loader. So they'll grab the chunk of data from the data loader and pass that as the input into the embedding table and then the transformer layers. So again, let me show you the diagram here. So that means those guys, the first stage, will grab the chunk of data from the batch, and will pass that data through the, as you can see here, embedding table, and only they have the embedding table, if you recall from the explanation back then. And then they'll pass the data through the transformer layers, and ultimately they end up with this with the output activations denoted in gray color here. Okay. And then all of the other stages will block on the communicate method, and that means they'll be waiting until the previous stage sends the activations to this stage, and then it will continue on the execution. So that means for these guys here, they'll be blocked until the gray activations are sent to the second stage here, and then they'll do the forward pass. Okay, so that's first thing. Then let's go back to the forward step. We have the forward pass through the model. So I'm gonna now just enable all of the breakpoints, and let me hit F5 just to enter into the actual forward pass. So I want to get, let me just do this. I'm gonna basically disable this and put a breakpoint here. So this is where the difference happens. So basically this is, as you can see here, GPT model forward. Depending on whether we're dealing with the last stage or any other stage of the pipeline, we'll be entering this branch here. And as you can see here, if I enter this one, this thing does converts the activations into the logits. So that means we'll end up with the vocab space dimensionality. So let me digest what I just said there. So if you take a look at the LM output, all of the stages will be just returning the pure activations. So that means 8,024, 1,024. So those are the raw activations from the transformer block. But the last stage will be returning this processed information, because it maps the tokens into the vocab space. Okay. So let me show you what I mean by that. So if we exit here, the outputs for the last stage will be, I think I have to do step over here, and then let's do output shape. So you can see here 50K. It will be 25K in the case of the of having sharded the model sharding, and yeah, that's it. So let me go outside of this thing, and now we're here. Okay, so now, again, remember, output is one of two things. It's either the raw activations from the transformer layer, or it's the tokens mapped into the vocab space for the last stage of the pipeline. And then the send forward, as you can see here, all of the stages will be communicating the activations to the next stage, but the last stage will just skip. As you can see here, if not the last stage, then communicate. If it is the last stage, we'll just ignore this. This is a no-op operation, no-op for the last stage. Okay, and finally, as you can see here, we have the last stage branch here, which means that the last stage will pass the logits into this function here and calculate the cross-entropy, and then it will return back the loss. Whereas all of the other stages first communicated information to the next stage, and then they return none. And then if we go a level up from this function, so this is the forward step, you can see that the output, again for the last stage, will be all reduced and then just added to this total output, which will finally return and use to calculate the perplexity, etc., etc. So hopefully that makes sense. Again, let me go through the diagram. I think it's fairly straightforward. So again, the first stage here will be grabbing the data from the data loader. It will be passing that data through the embedding table and then through the transformer layers until we have the raw activations, and then they'll be passing those activations on to the next stage. Whereas the next stage, we will be waiting for the activations and then grabbing the activations from the previous stage, passing those activations through the 12 transformer layers, and finally calculating the logits, calculating the cross-entropy loss, and then we'll be accumulating that information. If we were to have additionally intermediate stages in this diagram, obviously, then those would be receiving the activations from the previous stage and then just passing the activations to the next stage. So we kind of have three different branches in this pipeline logic. Cool, that was a long video. Hopefully you liked it. If you did, I would really appreciate any feedback. This will be the last video from the large language model series. I might create one more on the GPT-NeoX20B if I have any interest. If you'd like me to go through the GPT-NeoX20B codebase, do comment down below, and I'll be monitoring the comments. In any case, if you found this video useful, consider subscribing, sharing it out. That's the best way you can support the channel. And until next time, bye bye.